Well, that's a tough act to follow, and I'm honored to be following it. But in any case, good afternoon, everyone. I'm Mahault Albarracin. I'm the Director of Applied Research at Verses, and I'm finishing a PhD in Cognitive Computing at UCAM. I'm really delighted to be here with you today. In this talk, we're going to bridge most of the content that you saw being presented by Sean to cognitive science and mathematics. And so our goal is really to explore how we can take this rich phenomenological description of time consciousness and map it onto the contemporary framework of active inference. But then we're going to also extend this to how time consciousness can be shared amongst individuals in a group, leading to what we will call shared protensions. By the end of this talk, I really hope to show how these seemingly disparate fields can come together to give us really new insights into the nature of consciousness, social cognition, and collective behavior. So first, we're going to revisit quickly Husserl's phenomenology of time consciousness, but I will be quick on it. So at the core of this account, there are three components that Sean already went over. So the primal impression, which is our immediate experience of the present, retention, which isn't memory in the usual sense, but rather a still living preservation of what has just passed and that can be moved into sedimentation. It's really the just now that lingers into our consciousness. And then we have protension, which is the implicit anticipation of what's about to happen next. It's not necessarily an explicit prediction, but really an openness or expectation towards an immediate future. And so these three elements come together to form what we could call the temporal thickness of experience. And it means that our experience of any given moment isn't a thin slice of time, but really it has depth. It incorporates aspects of the just past and the about to be. And so this temporal thickness is really crucial in how we perceive and engage with the world. It really allows us to experience continuity and change, like as we saw, following a melody or coordinate our actions in a fluid, ongoing way. So now let's see how we can map those onto active inference by first exploring the key concepts that we want to leverage. To give a small overview, active inference in computational neuroscience and cognitive science models perception, learning, and decision-making as processes of minimizing surprise, or more technically, variational free energy. It posits that biological systems, including the brain, work to maintain their state within expected bounds by minimizing the difference between their predictions about their sensory inputs and the actual sensory inputs they receive. Observations are the sensory inputs that an agent receives from its environment. Hidden states are the agent's inferences about the underlying causes of their observations, the unobservable states of the world that the agent is trying to infer. The likelihood matrix captures beliefs about the mapping from observation to their causes, and it represents how likely certain observations are given particular hidden states. The transition matrix captures beliefs about the mapping between states at one time step and the states at another time step, so basically how the world evolves. There's prior preferences, which encodes the agent's preferences over outcomes, which drives actions. There's priors, who capture beliefs about base rates of occurrence of the hidden states, which basically capture the agent's initial beliefs about the world. There are policies, which are sequences of actions that the agent can take. So agents select policies that are expected to minimize free energy. There's precision parameter, which modulates the confidence an agent has in its beliefs versus new sensory information. Higher precision means the agent relies more on its prior beliefs. Expected free energy, which is what the agent expects to encounter in the future if it follows a particular policy. It's used to evaluate and select policies. The generative model models how the agent's beliefs about hidden states give rise to its sensory inputs. The recognition models is the opposite, where the agent's evolving beliefs about the hidden causes of its observations dynamically update based on the new data, and obviously variational free energy. And so the generative model uses the likelihood matrix to map hidden states to observations and the transition matrix to predict how states evolve over time. The recognition model is updated to minimize variational free energy, which measures the discrepancy between Q of S and the true posterior. Policies are evaluated based on their expected free energy, which incorporates the prior preferences. The precision modulates the influence of the prior D versus new observations, and the entire process operates in a hierarchical manner, as you can see in this example that was taken from Harvey Z and Sandbed. You can see that the agent starts with prior beliefs about hidden states. It uses those to predict observations through the likelihood. The actual observations are received and compared to predictions. The recognition model is updated to minimize free energy. And based on the updated beliefs, the agent evaluates policies using expected free energy. A policy is selected, actions are taken. This leads to new observations, and the cycle continues. So now how do we map this? Primal impressions really corresponds to the current and inferred hidden states in active inference. So just as the primal impression is our interpreted experience of the present moment, hidden states in active inference really represents the agent's best guess about the current state of the world based on sensory data. Retention corresponds to the process of updating and encoding new information in the generative model of active inference, and this process contributes to the sedimented knowledge represented by the model's parameters, including the likelihood matrix and the state transitions. And pretension aligns with the predictive aspects of active inference, and so agents continuously generate expectations about future states and observations, which are influenced by the retentions. So mathematically, the generative model is expressed as P of O and S equals P of O given S times P of S, which represent the mapping from hidden states to observations, and P of S encodes prior beliefs shaped by past experiences. So the relation of these terms gives us the overall probability of a particular series of observations and hidden states. So here, variational free energy, which quantifies the difference between predicted and actual states, is given by what we can call mathematically as F equals the expected value of log Q of S minus log P of S given O. So basically, this equation defines variational free energy as a measure of the difference between our beliefs and about the world and reality. So Q of S is our current belief about the hidden states, the recognition model. P of S given O is the true posterior probability of the hidden states given our observations, and E denotes the expected value. So the log difference between these probabilities is a measure of how surprised we are by our observations. Free energy quantifies how well our expectations match reality, and this is analogous to the fulfillment or frustration of pretension in Husserl's framework. Belief updating.
Sorry, I'll just take an opportunity that you've sort of reached perhaps a pause. Some people are saying they can't quite see the text, so maybe if we go back to, unfortunately, not having you with us in image and your screen, and you can share your slides a bit bigger, because I think at the back it's...
No problem.
Thank you very much. Sorry
Give me
for
one
that.
moment. How do I change this? How about this? Is this better?
It's totally white right now, but maybe...
Yeah, I don't know what happened there. Sorry, my bad. How about this? This is better?
Excellent, thank you.
Wonderful. So let's continue. Just a moment. Okay. So belief updating. Belief updating really is achieved by minimizing free energy. So Q of S equals the arg minimum of F. And this equation really describes how we update our beliefs in active inference. So the argument that minimizes F, in other words, we're finding the belief of Q of S that minimizes free energy. And so this process of continually updating our beliefs to minimize surprise mirrors Husserl's description of how our experience is shaped by the ongoing flow of retention, past experiences, primal impression, current observations, and retention, future expectations. So the overall process of belief updating mirrors the temporal thickness of experience. And so now that we've established this mapping, we can extend this to consider how pretensions can be shared among individuals in a social group. So In his later work, Husserl explored the concept of intersubjectivity, or how our senses of self and the world is co-constituted with others. And so building on this, we can conceptualize shared potentials as a form of co-constitutions where individuals in a group develop aligned expectations about the future. In the context of active inference, we can model this as multiple agents with overlapping or interactive generative model. And each agent's model now needs to account not just for the physical environment, but also for the actions and mental states of other agents. So to formalize this mathematically, we can turn to category theory, specifically the concept of polynomial functors, all of this pioneered by Toby Smith. And this allowed us to represent complex interactive systems in a rigorous way. And so for each agent, we can define a polynomial PI representing their interface with the world. And this polynomial encapsulates the agent's possible configurations and the inputs they expect in each configuration. It represents an agent's interface with the world. So PI1 is a set of possible configurations the agent can be in. And for each configuration J, PI of J represents the inputs the agent expects in that configuration. So the sum overall configuration gives us the complete descriptions of the agent's interface. The collective behavior of the group can then be modeled as a tensor product of these individual polynomials. So the tensor product over I of P sub I, this tensor product really represents how all the individual agents interfaces combine in the shared environment. It's a way of putting all the agent polynomials side by side to model their collective behavior. And so now we can capture how agents model each other's behavior, and we introduce the concept of a home polynomial. And so for polynomials P and Q, the home polynomial P and Q is defined, as you can see on line 1. And so this polynomial represents how one agent represented by P models another agent's behavior represented by Q. And so poly of P and Q is the set of all possible ways P could interact with Q. And for each possible interaction phi, we sum up all the inputs Q, which might receive based on P's configurations. This allows us to represent an agent's beliefs about how another agent will behave. So putting all this together, each agent's control system, alpha I, now has the type that you can see below. This describes the type of each agent's control system. It means that the agent's not only predicting its own actions and observations, but also modeling how it interacts with all other agents. This formulation means that each agent isn't really predicting just themselves, but also all of their agents and their predictions along with their actions. So we now have a way to model how individual pretensions can align and interact within a group, leading to shared expectations and coordinated behavior. This captures the essence of how we, as social beings, don't just anticipate our own future. We continuously model and anticipate all of the actions of everything around us as well. So then we're going to use sheaf theory to model how these individual perspectives can converge into a shared understanding. Sheaf theory describes how local information can be consistently integrated into global structures. So a sheaf is a mathematical object that tracks how local data can be reliably combined into global data. And this makes it ideal for modeling how individual agents' perspectives can come together to form a shared understanding. So in our framework, we can think of each agent's world model as a sheaf over their perceived space, and each agent has a local knowledge and expectation about different aspects of their environment. The sheaf structure allows us to formalize how these local pieces of information relate to each other and how they can be combined. Developing shared protension becomes a matter of gluing these individual sheaves together, and this gluing process is a key feature of sheaf theory. It allows us to take consistent local information and combine it into a larger coherent structure. So if we have a collection of agent world model X of J, each including a topos space X of J, we can attempt to glue these into what we will call a consensus topos space W. And so this space W represents the shared understanding of the world constructed by the group. The consensus topos can be thought of as a kind of shared universe of discourse for the agent. It encapsulates their collective understanding and expectations. This shared universe isn't just the sum of individual perspectives, it emerges from their interactions and mutual adjustments. So if the gluing process is successful, it means the agents have achieved a consistent shared understanding. But if not, it points to areas of disagreement or inconsistency or frustration in the group's collective model. And so this sheaf theoretic account models how individual agents, each with their own perspective and expectations, can come together to form a coherent group with shared potentials, and allows us to formally describe the emergence of collective intentionality and shared goals. And so to conclude, this has really interesting implications. It offers possibilities. For instance, the computational framework now has a mathematical account that can go a little further than the previous accounts. We can use this for sophisticated models of social cognition, collective behavior, and also potential for applications in artificial intelligence for systems that can better model and interact with human social dynamics, especially. Thank you.